I'm glad you're not all worn out yet. I know you've been to like a million lectures. This is kind of light today, so I'm doing RLC curves and I'm going to get started on GAMs. Okay. So in machine learning, one of the biggest things that we're concerned about is how to evaluate the quality of our results. Because we very often design algorithms that try to aim for, whatever quality metrics we're defining. And so we often use classification error, which is just, the fraction of points that are misclassified. But just as often, in fact, maybe even more often, we use RLC curves in the area under the RLC curve to measure performance of machine learning algorithms. So almost every paper on classification that you'll read has some sort of reference to RLC or HC. Okay, so let's go back to classification. So you have all of these observations, which are sometimes called examples. So this is X, and then you have also Y, which are the labels. And then you have your predictions, which are often real valued things. So in decision trees, these are probabilities, right? These are like, the fraction of stuff in the leaf that, examples in the leaf that are positive. If you're doing logistic regression, you'll get like a score, like a number like this. And then to create a classifier, you would create a threshold. Like for decision trees, you'd say, okay, if more than 50% of the examples in the leaf are positive, I predict positive, right? So that's a threshold that you're putting on that at the 50% mark. With a regular classifier, like a logistic regression classifier, you again have to place a threshold and say like, above this number, I predict positive, and below this number, I predict negative. And the nice thing about the RLC curve and the area under the RLC curve is that it doesn't matter where you put the threshold. This is threshold independent. Okay. So anyway, you have your predicted labels, which is that you take f of x and put a threshold and then vote positive if it's above the threshold, vote negative if it is below the threshold. And here the threshold is just 0. Okay, cool. So now I am going to ignore everything except the labels and predicted labels. And what I'm going to do here is I'm just going to work with those for a little while, and then I'll switch it all up, okay? So if the classifier is really good, these columns agree with each other. All right, so I'm just going to add a few more examples there just for fun. And I want to point out that this is what's called a true positive, because you predicted that it was positive and it actually is. This is called a true negative, because you predicted it was negative and it actually was. This is called a false positive, or a type 1 error, because you predicted that it was positive, but it is not. And then this is called a type 2 error, or a false negative, because you predicted it was negative and it actually was not. So what we want to avoid are mistakes. And these are the two types of mistakes we can make with a classifier. Okay, so great. So what we have, this is called a confusion matrix. And the confusion matrix lists the true positives, false negatives, and true negatives. And so what you really want is for these two numbers to be large, and you want those two numbers to be small. Okay. So the standard misclassification error is just a fraction of points that are either false positives or false negatives, right? That's just standard misclassification error. And you can write that also as like a fraction of points that are misclassified. So this is the fraction of points where y doesn't equal the predicted y. Okay, so that's fine. You just add up the false positives and false negatives. But there's also like a lot of other statistics you can compute from the confusion matrix that are used in practice. So this is called the true positive rate. So it is the fraction of predicted positive and true positive. Okay, so it's this guy, TP, divided by the sum of these two, okay, divided by the total number of positives. All right, so true positive rate is true positive over the number of positives. Okay, and there's a whole bunch of these things. I don't really want to go over these in detail because there's no way you can remember all of them, but I just want you to know they exist. So this is called the true negative rate. So it's the fraction of true negatives over the number of negatives. And then there's the false positive rate, which is the number of false positives over the number of negatives. You get the point, hopefully. Okay, this one's called precision, which is the fraction of true positives over predicted positives. So precision is often used for like measuring the quality of a search engine, because it's like, okay, I returned 10 results. How many of them are actually useful with respect to the query, right? And so that's the precision. And then we also have, there's also other ones like recall, and like it just gets, well, actually recall I covered already. No, did I? Yeah, recall is this one. Recall is of the relevant web pages, how many of them did I return? Okay, so you get the idea that you can take this confusion matrix and compute a whole bunch of statistics from it. Okay, and so now you know what true positives and false positives are. Good. Okay, so now that you understand confusion matrices, I can talk about RSC curves. So RSC curves, just to give you a little history, RSC curves started during World War II for analyzing radar signals. So what happened was that there were engineers that were like working on these, they had these radar detectors for aircraft, and they realized that, models with different true positive rates can't actually be directly compared because they might have different false positive rates. Okay. So after Pearl Harbor in 1941, the United States Army wanted to detect like the Japanese aircraft from their radar signals. And so they measured like the ability of the radar receiver operators to detect the Japanese planes using these curves, which we call receiver operator characteristics. So basically you had this knob, and if the knob goes one way, they could detect all the Japanese aircraft and a whole lot of garbage. Like just detect lots of stuff. And so then it was very difficult to figure out which ones were real and which ones were not. And if they turned the knob the other way, they would detect nothing. Okay, so you had to get like the right spot so that the true positive rate was high, but the false positive rate was low. So that's what the whole idea is here, is to calculate for a particular false positive rate. So a particular way of turning that dial, what is the true positive rate? Okay, and so again, false positive rate, that's the fraction of negatives that are classified by the machine learning algorithm as positives. Okay, and then true positive rate is the fraction of positives that are classified correctly as positive. Okay, you all understand the idea here? Hopefully, okay, great. So anyway, so let's go with this example here. So here is my data set. It's all along one dimension here. The classifier predicts more positive this way, predicts more negative that way. And the true positive rate is 7 out of 11. So how do I know that? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 7 of the positives are on this side out of the 11 positives. And then for false positive, I have 3 out of the 12 negatives that are on the board that are predicted positive. Okay, great. Now, if I fiddle with that decision boundary, so if I put the decision boundary up a little higher, then my true positive rate and false positive rate change. So here I've got only 3 out of my 11 positives and 2 out of my 12 negative predicted positive. Okay, and I can do the same thing by moving it this way. So here 10 out of 11 positives predicted positive and 7 out of my 12 negatives predicted positive. And so now, as you can probably figure out, what I'm going to do is take this decision boundary and just try every possible value for it. I'm going to shift it in every possible way so that in some sense, I'm looking at every possible decision boundary I could put in here. And I want to discover more positives before I discover the negatives when I'm doing this. Okay. So as I go from here to here, it would be good if I hit all the positives before I hit all the negatives. So then what I can do is for every possible value of that decision boundary, I can plot the true positive rate and the false positive rate and get a curve out of it. Okay, so what I would do is as I change this, as I move this thing down, every possible spot that I can move it to, right here, 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 I'm going to write down the true positive rate and the false positive rate and plot it on the curve. Okay, so I'll do that. And I'm just making up this is just an illustration, but you would just plot it for every single value here. And then you connect the dots, and that's called an ROC curve. Okay? Yeah.
Is ROC curve always done with the line horizontally, not vertically going to the points?
Oh, it's just so, all right, that's a good question. So what I was just illustrating is just a single function here, and the function that I happen to create as my classifier only varied along this one dimension. But it's, you know, in high dimensional space, you'll have literally a function that gives a real valued score to each data point. And what you do is you just take that function and decrease it from its maximum value down to its minimum value. And every time you cross a point, you'll update, you'll have a new point on the ROC curve for true positive and false positive rates.
Okay, so it can be any function.
It can be any function in high dimensions, as long as it provides some kind of score for each data point. Okay, great. You can see why I'm illustrating it in one dimension. It's just much easier to sort of visualize what's going on. Okay, so that's called an ROC curve. And then the quantity that we actually really care about is the area under this curve, okay? So the area under this curve is the quality measure for our classifier, our real valued classifier. Now, if the classifier was really, really good, it would hit all the positives first before it hit all the negatives. And so its true positive rate would stay up at 100% before it hit any of those negatives. So the best possible thing you could get is to go up and over. And the worst possible thing you can get is to be on this line. Now, if you happen to see an ROC curve that is below the line, which does happen occasionally, we do see that. If that happens, you might want to turn your classifier upside down because your classifier classifies negatives higher than positives consistently. And in which case you just flip it upside down and then its ROC curve will be better than that line. And so your classifier is better than random. So what's the worst thing you can get is to have the false positive rate and the true positive rate increase at the same rate. And when that happens, you know that your classifier is just like random guessing. Okay. Now, yeah, so here what I was showing you is like rates, like true positive rate and false positive rate. Yeah.
If you have different proportions of positives and negatives, do you have to scale for that?
Yeah, it's all scaled because these are rates. So this is between 0 and 1, and this is also between 0 and 1. So everything is divided by the number of positives and the number of negatives. But I'm really glad you asked me that because I'm going to remove that scaling in the next slide. Okay, so I'm going to do it without the scaling on this slide. Okay. So now all I have is here 0 to number of positives and 0 to number of negatives. Okay. So when I do this, I'm going to grab these are the values of my function. So for the question that you asked earlier, so all I need are the values of this function, right? I don't really need to know anything else. I don't need to know what geometry it is. I don't need to know anything. I just need to know what predictions it's making for each data point, okay? So I take those predictions and then I take the labels, okay? That's all I need to compute the ROC curves, okay? So this is my predictions. This is my labels. And I'm going to create kind of an unscaled ROC curve from this. And the way I'm going to do it is by changing the decision boundary here, 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 here. Okay. So when I do that, the first thing that I see is that my first point is, unfortunately, my top rated point is a negative. That's bad, right? We're supposed to have positives on top, but it's negative. So what I'll do is move my RSC curve one in this direction. I have one false positive. Okay, then I have two positives, so I'm going to go up two. And then I have a negative and a positive and three negatives, a positive and a negative. Okay, so this is the unscaled version of my RSC curve. Okay, so to get a regular RSC curve from this, again, all you do is divide by the number of negatives and divide by the number of positives on this axis, and that's the RSC curve. Okay, now if the RSC curve is really good, then I would have seen all the positives before I see the negatives. And so I would go like this: positive, 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 negative, 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 negative. Oops, sorry. I got a little excited there. Okay. And then if it's really bad, then I'm doing basically random guessing, which is kind of similar to just alternating. And then in that case, the true positive rate increases as the false positive rate, and thing goes along a diagonal. Okay. So now that you know how to plot RSC curves, you could plot them for different algorithms and see how those algorithms look. So this is, for example, 7 different RSC curves from 7 different algorithms. And what you can see here is that some of these algorithms do better on like the very top part of the ranked list, like where the, at the very high levels of f of x, and some of them do better with lower levels of f of x, okay? So you can, by changing which classifier you're using, you can see different RSC curves and the way they perform. Now,
Cynthia?
Yeah.
So can you compare ROC curves for the training and the test set?
you can, we do that all the time. And if it generalizes well, those curves should be on top of each other.
Okay, so that's a way to check generalization.
That is exactly a wonderful way to check generalization, and we do that in almost all of our papers. Okay, great. So I want to point out that if you're a statistician, you might get really excited about the AUC because it's what's called a rank statistic or a use statistic. So what I want to point out is that if you take a pair of points here, that corresponds to 1 square under this RSC curve. So let's consider this point 10, whose label is that's predicted. Its predicted value is 10, like its score is 10, and its label is 1. So it is the second positive, 1, 2, and it is the 1, 2, 3, 4th negative. 1, 2, 3, 4. And so that pair corresponds to this area under this curve. So the area under the RSC curve essentially counts the fraction of positive negative pairs that are correctly classified. So in other words, such that the positive is above the negative. So here, this positive is above that negative, and so this is under the RSC curve. Whereas like for a pair of points here, like this positive and that negative, the negative is actually earlier, like has a higher score than the positive. And this doesn't contribute to the RSC, the area under the RSC curve. So this area you should think of as like, you're counting sort of positive negative pairs that are correctly classified. Okay, so because it's using pairs, it is, it's using pairs where one is ranked above the other. It is a ranked statistic, or what's called a use statistic. So statisticians get very excited about this. Okay. So so the area under the RSC curve is the fraction of correctly ranked positive negative pairs. And so you can think about it as 1 minus the fraction of misranked positive negative pairs. Okay. So you can think of it as like one minus some kind of misranking error. Now, I think for me, one of the major uses for RSC curves is to do data exploration. So if somebody hands me a data set and I've never seen it before, and it's like a tabular data set, what I'll very often do is consider each feature as its own model. So it's like, you gave me a data set with like 20 features. I'm going to take each one of those and use it by itself as if that feature were the classifier. And so I can produce an RC curve for every single feature. So what I'm showing you here is the RC curves for each of the 8 features in the Pima Indians diabetes data set, where you're trying to predict whether someone will have diabetes. And what you can see here, I mean, there's a lot of things that I can tell you about this data set from looking at these RC curves, okay? I can tell you that there is one feature that is really good. I don't know which one it is because I didn't write it down, unfortunately, but I know that there's one feature that's just better than the rest. Okay, what else do I know? I know that there are these 2 features that are probably pretty correlated with each other, but they're not totally correlated with each other, so they could both provide valuable information. And they're both really good sort of they're not great toward the top of the ranked list, but they're pretty good toward the middle and the bottom of the ranked list. Okay, so in other words, the score values sort of in the middle toward the bottom are actually quite valuable for helping you decide which person should be ranked above another one. I can also tell you that there are some features that are not very good. I don't know if those will be valuable at all. I'm not sure. Or at least they're only, well, maybe the green one's only valuable for people who have high scores, and the purple one as well. Like, but the thing is that none of these are sort of, well, I guess the red and the orange might not both be, you might not want to put both of those in the same model because they're very highly correlated with each other. Okay, so hopefully this gives you a sense of like what you can do if you know ROC curves. Now that you know ROC curves.
Another question.
Yeah.
I was wondering for these, when we have different features, and do we have to, they could have like different axes for their scores. Do we ensure some sort of monotonicity because there's a ranking involved, that a smaller score, say, corresponds to negative labels and a higher score? Say if the feature instead of maybe height, it was like, I don't know, 100 minus height, or do we have to do some like pre-processing for a plot like this?
No, I mean, all I did was just rank all the observations by their feature values, one at a time. Okay, so I took, maybe this might be the age feature, I don't know. Okay, so what I did was I just ordered everybody by age, and then took the Y values from there, constructed the RC curves from those Y values. That's it. Done. It's not any more complicated than that. So, and if you're using sort of like MATLAB or what other Python or something, you would just issue a command, say, plot RC curve feature Y. Done.
If that's how we're doing it like that, like you showed with the steps, and how come the curves don't look like they're steps anymore?
Because there's a lot of data.
Okay.
Yeah, there's a lot of data. If you break it all the way down, then you will see steps.
Okay.
Yeah, but sometimes you see diagonal values because if there's a tie, it creates diagonal. So it could be that everybody who has a low value of this all has the same value, like it's all 0 or something like that. So you might see a curve like that for all 0. Yeah.
Yeah, so this is for binary classification essentially, like if you have multi-class, is there, or do you just do it pairwise?
You would do it pairwise for multi-class. There's, as far as I mean, maybe somebody has come up with an analogy for RC curves for multi-class, but I don't know exactly how you do it. Yeah, I would do 1 versus all.
Okay.
Yeah. Okay, great. All right, and then if you take these features and combine them together, you would expect that you could get a classifier that's better than any of the features alone, right? And given the fact that these features are all different from each other, you would expect that you would get a really good classifier over here. So let's show you what happens if you do that. Here is, this is the boosted decision tree classifier for this data. And this is a combination of decision trees. It's a weighted combination of decision trees, and it produces a beautiful result that's quite, you know, very good classifier in that sense. Okay, cool. All right, so just to review what I've taught you so far today. I've taught you the many different ways to evaluate a machine learning model. If you have a decision boundary, you can create a confusion matrix. If you have a confusion matrix, you can calculate the true positive, true negative, false positive, and false negative, and there's lots of statistics you can compute from them. We can always use accuracy, or 1 minus accuracy, which is classification error. I've also taught sort of precision and recall that you can get from those guys. And then I taught ROC curves and area under the ROC curve. Do you have any questions before I switch over to a new topic? Yeah.
Just one last question for the class, when we took each feature as a classifier, in case of like categorical data, is there ever a challenge in assigning the score? How do we handle that?
So if you have a binary variable, so like, color equals blue, then what would happen is the RC curve has a lot of ties in it. And so you end up with a curve that looks like diagonal and then diagonal. So you'd see if you have a lot of binary features and you did this, you would see bump, 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 like that. Yeah.
So when you're showing us the, I think you called it the ranking statistic, and the fact that the best classifiers would have these kind of pairs ordered correctly, are there any algorithms that are motivated that way?
Yes, there's an entire field of machine learning called supervised ranking. I spent a good chunk of my life working in supervised ranking, where the goal is to simply try to improve the number of positives that are ranked above increase the number of positives that are ranked above negatives, to try to optimize the area under the ROC curve or weighted areas under the ROC curve. Yeah, I can talk to you more about that offline, but yeah, there's a whole field of machine learning that deals with that. And that's particularly interesting for people who build search engines, because they really only care about the top 10 results that they provide you, and they don't care about the ranking of all the other stuff that they're not going to give you in the first page of search results. And they have their own interesting rank statistics too. DCG, discounted cumulative gain, normalized discounted cumulative gain. There's a whole bunch of them that these guys care about. Yeah. Good questions. Okay, great. Cool. All right, so I'm going to switch over to generalized additive models, which is the last topic that I want to convey to you. And so I'll be spending the rest of this lecture and the next lecture on GAMs. Okay. Okay. So as I mentioned, GAMs are kind of the opposite of decision trees. Decision trees have a lot of interaction terms between variables, they're basically all interaction terms, whereas additive models have no interaction terms at all. Each feature contributes separately. So this is the kind of thing that an additive model does. It says that the predictive label is related to the sum of terms. You have one term for each feature, and these terms, these FJs, can be nonlinear. So that's what's interesting about GAMs, is that they can produce nonlinear functions of the original variables, but they get added together in a linear way. Okay, so for instance, if x1 is age, well, this function increases with age, and then you add it to what, I don't know, I should have done this one blood pressure and that one age, I don't know, whatever, but you get the idea. You're adding up these functions of the original variables, and that's what's comprising the GAM.
So do you really mean Fi of Xi, or do you mean Fi of X? Why are the subscripts of X changing with the F subscripts of the F?
So what I should have done is put a dot here. So
Right.
This is the first feature,
Right.
and I have a function of the first feature only.
Okay.
Yeah. So I should have put a dot to just reserve a spot for the observation index, but this is supposed to be the first feature. Yeah. Okay, great. Okay, and yeah, so the nice thing about this is like, you can do things like saturate, like if you say, you know, how much school have you had? Is the amount of schooling likely to help you reduce your probability that you'll commit a crime? Well, you know, if you've had at least college, then maybe your rate kind of flattens out, right? So you get this kind of saturating effect, or like maybe by the time you're 35 years old, you don't want to commit any more crimes, and it doesn't matter how much older you are than 35, it doesn't really change. Okay, so stuff like that. Okay, and the way that I'm going to construct these curves is actually with dummy variables. So my models, they're comprised of these step functions. Okay, and you don't always have to use step functions. I'm just going to use them because I like them. All right. So these are like little steps, and you add them together, and you get kind of these like little staircases as our functions. And you can have these things going up. You can force them to go down. So you can make them monotonically increasing, monotonically decreasing, or you can let them be free and do whatever they like. Okay, and I have to use my machine learning algorithm to figure out where all of those steps go and how tall they are. So I'm going to teach you boosted stumps, which is actually a simplified version of boosted decision trees. And at each iteration, the algorithm is going to pick one of the features and a threshold. So it's going to pick like one of those steps and create it. And it's going to add the steps one by one. Okay, so this is feature 10, and it's going to create a step on feature 10 that's of height alpha 1. And then I would add to that a step of size alpha 2 on feature 3, and then I'm going to keep going like that. Okay, so I'll keep adding that. And oh, by the way, I meant to say, this is actually a binary feature. And so what I'm doing is saying, if the feature is 1, then I will add alpha 2 points. If the feature value is 0, I will add no points. Okay, great. So I keep going like that and adding these things together. And then after I add a ton of stumps, I just sort them by feature and add them up. Okay, so if I have, like if these are all of the steps that I added in all of my iterations, then you can see I've sorted them by feature. Like this, these are all the features. This is all the steps that I created for feature 1. And these are all the steps I created for feature 2 and feature 3. And then like I added this in the 6th iteration, the 12th iteration, the 94th iteration, and so on. And so I'm just going to add them up. And then I'll get these like nice little staircases like that. Okay. So, and then here's, you can see that, what I want you to notice what I did here. So all of the steps here are facing this way. So they're all increasing. So that means the function is going to be monotonically increasing. And then here, these steps are all steps down. And so these are all going to be decreasing. So the function is going to be decreasing. Okay. And then this function at the bottom is going to be increasing 2 steps and decreasing 1 step. And so you can get something like that. Okay. All right. So these are my component functions there. Yeah, so you can force it to use step functions that face different ways. And if you're using standard algorithms, it's really easy to sort of force these steps to face different ways if you want the functions to be either increasing or decreasing.
So how are you choosing how many iterations you need?
I'm going to do it until it converges.
Okay.
Yeah.
So don't you just have a set of functions that are, so you have a set of functions that are defined on the data points, non-negative functions that are defined in the data points. Isn't that what you have? And then you're just examining all of them.
Yeah. So what I'm doing is, so let's say X1 is age. Then I would create a step for between every possible 2 ages in the data set. Right. And then I can create a step on every, in between every 2 ages. Yes, that's right.
And how are you choosing the weights for each step?
That's exactly what I'm going to tell you about. I'm going to do it to minimize the exponential loss. Yeah, and that's what the rest of this lecture and next lecture is about.
Another question is, does it matter the order in which you do this? I mean, you said you did something at the 39th step or something. What happened if you did it at the second step?
Yep, so all of these decisions are going to be made by an algorithm to minimize some objective. And so it doesn't matter in which step these decisions are made, but the decisions will be made to try to minimize some objective.
But
Yeah.
you are assuming an order on the data points, right?
That's irrelevant because every step is going to use all of the data points. It's just going to use one feature at each iteration, right? So it's going to pick like, okay, age less than 30. And then it's going to include a step function for age less than 30 at that iteration.
And then what would the next iteration be?
It might be like blood pressure greater than 50.
Ah, okay.
But you're saying it doesn't matter the order in which you do that. You get the same result because you're using all the data all the time. It's
That's
not
right.
as though you're selecting some data at each step to make a
Correct.
change.
Correct.
Right, okay. You're just
You're
doing
using-
it one at a time to make the calculations easier. But
That's right.
manageable.
Yes.
Right.
So I'm doing this. So I want to, I want to construct something that looks like. I want to construct something that looks like this, right? And this is, one feature, second feature, third feature, fourth feature. I have to construct it somehow. And so I'm going to construct it by creating one step at a time. And every time I add a step, I use the whole data set to help me figure out what step to add. And I'm going to do it to minimize some function that I haven't told you what it is yet, but I will. Yeah. Okay, great. All right, good. Okay, so yeah, so what I'm doing is essentially just taking the iterations, taking all the step functions that I get at each iteration, and then sorting them by feature to get these functions. I think I've made that point already. So I'll maybe skip that. Okay, so this is an example of one of these component functions. This is from a paper of Rich Caruana, who he loves GAMs. He's been working on GAMs for at least 10 years, and his GAMs are beautiful. So this is one of the functions that he created for a pneumonia risk score, and it is a function of age. And what he pointed out when he gives talks, he points out that there's something funky going on where at around 67 years old, there all of a sudden the pneumonia risk goes up. And he was saying, I don't know why that's going on. He said, don't worry about all this stuff, because this stuff is for, this stuff, I don't know how much data you have for people who are between 90 and 100 years old, but let's not worry about that. Let's worry about this. And he says, look, something, I think what might be going on is that this is people retiring. And then because they're retiring, they don't maybe do as much exercise or whatever, and so they have a higher pneumonia risk. And that's reflected in this component score. And so the idea is that if you look at this thing and you go, oh, look, but maybe there's a retirement effect, then it would be nice if you could sort of put in a new feature, which is retirement age, in which case that feature would have like a bump in it, whereas this feature might be a little bit smoother. Okay, so that's the kind of thing you can try to get from GAMs. All right, so what I'm going to do now is I'm going to switch over to the iPad. I would feel terrible if I stole my kid's iPad and not used it. So go over here. Oops. Oh dear. Figure out how to do this. Lovely. Oops, what's going on? Cynthia?
I have a question. Oh, sorry, I'm like
Yes.
interrupting you.
We're good.
So why not use smoother function and step functions? Is it because you like step?
You can use a smoother function. I happen to like the step functions just because I feel like they're simple. But you can definitely use a spline or, whether you can use a polynomial or whatever you want. I like the step functions because they're very, very flexible. They can give you any shape. You know what I mean? You can think about how they would be if they were smoothed out, but the truth is they can give you any shape, that you want. And also you can convert them to points. So you can, instead of drawing it as like a step function like that, you can actually convert it to a table where you can look up how many points you get depending on which step you fit into, which steps you satisfy. Yeah.
So I guess there's no assumption that you need to do calculus before, because I feel like the step function then would be, if you have to like say, take a derivatives and so on, like the step functions would be problematic in that case, right? Or do you not have such operations?
There are derivatives in the calculation that I'm going to do,
Okay.
but how do I say this? Not over that step.
I see. So you just sort of like the points where you have that would not exist, you just won't consider them.
Say that again.
The points where the derivatives would not exist, you just sort of like not consider them.
Oh, those. So okay. So if so, what you do is, so let's say that you have age, right? Age is one of your variables. So you have like age. So you have, let's say you have people in your database with every age, so 29 and 30 and 31, right? Like this. So you'd create thresholds kind of right in between. So you'd have age greater than or equal to 29.5, like this. And then if you had a new person who shows up and they're at 29 and a half, they're right on that line, they're still okay. There's still a prediction made for them. Okay.
To me, it was very similar to linear regression, but is that because we have like f of x, so we can also select the like nonlinear functions, right? So is that kind of a generalization form of linear regression?
Well, it's classification. So for linear regression, we usually have real valued y's. And then we would use a squared loss like this, yi minus f of x I squared, right? That would be our loss function. But for classification, we want to consider loss functions that are kind of like 1 if yi doesn't equal the sign of f of xi. So the loss functions are different, and here the labels are y are in, when the yi's are in plus or minus 1. So that's the difference between classification and regression. If you're thinking about logistic regression, it is a classification algorithm.
Yeah, I that's that function in general, like a decision boundary. Like the decision boundary is like it's kind of like with features, like we have like coefficients for each feature, right? But these coefficients can be like, it's not only like like it's not the coefficients could be functions like at any form in that sense.
Yeah. Yeah, I mean these component functions can be, whatever. Yeah. Okay. Cool. All right. So I'm going to start with just defining classification error, which I have sort of right on the board here. Okay. So my handwriting is quite so messy. So I'm just going to sum over I. 1 if, and I've forgotten the 1 over n, and the reason I did that is because I always forget it. And so if I forget it, if I put it in now, then the rest of the calculation I'll leave it off, and everybody will get confused.
So we're not seeing anything on the screen. So
Oh, that's strange.
Try unplugging it and plugging it back in your iPad. Yeah.
There we go.
Great.
Wait, but it's not plugged in.
You have to give it a second. It is a little slow.
Oh,
We did see something for a minute.
but I was holding the cord.
Be a little patient, unfortunately, sorry.
Magic.
Electric personality.
Oh, yeah.
Oh, that was so fun. Okay. It's like, you know, okay. I've seen a ghost. Okay. All right, and then f of xi, of course, is a sum, j equals 1 to, and I'll tell you what j is in a second. Alpha j, hj of x, okay, and then here my, these hj's are like, you know, h of age of some other variable. And this is age, and some like function like that. Or it could be, you know, an increasing function of age or whatever. Okay. And this j here, that's the number of thresholds for all features. So it's the total number of these little threshold features we can create. All right. So then I can write down that my classification error. Sorry, I'll just copy that. Is 1 if sum of times that y does not equal the sine of f of x. Okay, and then I can also write this as sum over I, 1 if yi times f of xi is less than or equal to 0. Okay, so why is that true? So if you think about y and the sine of f of x, and then you do y times f, well, plus minus, put in the whole truth table here. Okay, and then so y times f is positive, positive, and then negative. Okay, so hopefully you guys can see that. Okay, so what I'm going to do next, this thing over here, this is a function that is 1. If you plot, this is y times f of x, this is called the margin here. This is 0, that's 1. And this is a function that is 1 if the margin is less than 0. Okay. This is 1 if yi times f of xi is less than or equal to 0. Okay. So this is the misclassification error. If you are on this side, you are misclassified because your y does not equal the sine of f. And if you are over here, you have a positive margin, your y and f have the same sign. So these are correctly classified points. These are incorrectly classified points. Now, this function, as you can see, is not differentiable. And so trying to minimize a function like this that's not differentiable is really difficult. Okay. So what we're going to do is upper bound this thing by a function that is smooth and convex and take derivatives of it. Okay, so I have my function here that is like that. And I'm going to create an upper bound for it like this. Okay, so this function it's e to the negative z. Okay, or e to the negative something on the margin. So this is y times f. I apologize for my messy handwriting. I'll try to make it a little tidier. Okay. There we go. Okay, great. So this is e to the negative y times f. Okay, actually, I don't need i's over here. Oh boy, my eraser is not the right size. There we go. Okay, so what I'm doing is taking an upper bound, which is e to the negative yi f of xi. Okay. And then I can write this as the sum over I, e to the negative yi. And then f of xi again is the sum over j alpha j of hj of xi. Okay. So what we're going to do then, hopefully everybody kind of understood that. Again, apologies for the super messy handwriting. So we now have the objective that we're trying to minimize. And the idea is that if we can pick the alphas and the set of j's to make this small, we will be minimizing this, which in turn minimizes this, right? So if we can make these guys, like, let's say all of the values were down here, then all the points would be correctly classified, right? So we want to make the exponential loss as small as we can get it. And that will in turn make if we make this small, that'll also make this small, because it's a lower bound for it. Okay. Is everybody kind of following me? If you're not following me, let me know and I can explain again. Okay, great. Okay, so what we're going to do is at each iteration, we're going to choose hj, so some function hj, which is one of these step functions, and an alpha j that most decreases the exponential loss. That loss. Okay. Great. So so again, hj is going to be some like step function of like age, perhaps. I don't know. Make that a little more tidy. Like that. Some step function of age. And you'll pick some step function at every iteration and some alpha to try to make this smaller and smaller and smaller. Okay, and this algorithm that does this is called boosted stumps. Okay. This is boosted stumps. All right, now you've noticed maybe that I haven't said anything about the number of terms here, because if you're just minimizing this, then you can have a very, very large number of terms here, which is not really what we want for interpretability. So for interpretability, we have to not only consider this, we also have to consider the total number of terms we're including in our model. Okay. So if you're really good at optimization, right? If you know how to optimize, like if you can optimize, what you actually want to solve is this problem. And I'll use a different color just to, that's min over all functions f, sum over I, e to the negative yi f of xi, plus, and then we'll put a constant here. This is a regularization parameter. I haven't defined this norm yet, but you can probably figure out what it is. Okay, but let me first define f. So f is a linear combination of these alpha, it's a linear combination of the hj's. And again, hj, one of these hj's is like 1 if age is greater than or equal to 30, something like that. And then this 0 semi-norm is the number of non-zero alpha j terms. Okay, so this is actually the problem you want to solve. Okay. So then if you manage to solve this, be good at optimization, you can solve this thing. Then your f of x will be a sparse combination of these step functions. and it will look happily like exactly what we want. Now this involves a best subset search. Because we need to figure out like which are the steps we actually need, like what is the subset of steps we actually need in order to optimize this thing. Okay. So the problem, the algorithm that there's a few algorithms that solve this problem now. And the one that I'm going to talk about, although I'm not going to give too many details on it, but the one that I'm going to talk about is an algorithm called fast-sparse. That solves this optimization problem. Okay. Do I have any questions on why we're trying to do this? Okay, cool. So I want to point out that the exponential loss actually has some really wonderful benefits. So here I'm using the exponential loss, and you're probably thinking, you know, I mean, there's a few other loss functions that I could have used here. Right, all I needed in terms of the loss function was that it had to upper bound this function that is, you know, 1 sometimes and 0 other times. I just needed an upper bound for that. And I needed it to be convex. So you could use the logistic loss that Leslie talked about to you guys the other day. Or you can use, there's many different functions like this, but this one has a lot of really nice benefits to it. So what I'd like to do is just talk for a bit about what these benefits are. And I won't have time to finish this, but that gives me a chance to review it at the beginning of the next time. Okay. So, cool. So I'll write here, and maybe I'll just switch colors for fun. So the X blocks has several benefits. Okay. So the first one is that it is convex. Okay, convex functions are nice because any local minimizer is a global minimizer. So it's very easy to work with convex functions. Right, neural networks are not convex, which is what causes the challenges with convergence of them. Whereas exponential loss is convex, so that you're pretty reliably going to get to a good solution when you use exponential loss. It has an analytical solution for the minimizer. So if you want to get to the bottom of some kind of exponential loss, you know, this thing, this guy over here. If you want to minimize this with respect to one of the alpha j's, there is actually an analytical solution. You can write down a formula to do it. I'm not going to do it. I'll just write not today because it involves quite a lot of notation. Okay. And then another thing about the exponential loss is that there is a natural conversion to probabilities. So when you have a function that minimizes the exponential loss, you have this function that minimizes the exponential loss, then you can convert it to the probability that y equals 1 given x. And there's a formula to do that. And so I've now previewed exactly what I'm going to do next time. I'm going to prove to you that the exponential loss is convex and that there is a natural conversion to probabilities, and I'm going to derive that formula for you next time. Okay? Yeah.
Is this related to softmax?
This conversion is the conversion formula that does that actually converts real valued functions to numbers between 0 and 1.
Right.
You can think of that as looking like a softmax. Yeah. It is a softmax function that does that conversion. Yeah. Yeah.
So you have an analytic solution for this? How well does it compare to the original problem solution?
Well, I mean, we only have an analytical solution for updating one alpha at a time.
Okay.
So it's not an analytical solution for the whole thing.
Okay.
Yeah, it's
Can you
just a,
compare?
yeah, you, what?
Can you compare, like, can you get a, how close is the true solution if you had solved it with the indicators?
Well, it's hard to solve it for the indicator, so that one's very difficult to figure out.
Yeah, it's just that, like in RL, it seems like they have, like I learned it this way too. In RL, they seem to be going back to the indicator function.
Oh, interesting.
Like they don't, the upper bound is like really bad for some reason for them, and they solve it using indicators. Yeah, so I was curious.
So for these, it's not bad at all.
Yeah, these are not bad, but like for classification, it's not bad, but for some reason, like in the RL, all their problems are in as indicators. They go back to the probabilistic.
I don't know why that is.
I was just curious.
These upper bounds are they're very good.
Yeah, in classification, yeah.
And the performance is often better using the upper bounds than 0, 1, because the 0, 1, you have a lot of trouble optimizing it.
Yeah.
And so when you optimize the upper bounds, you actually get a better 0, 1 loss than if you optimize that directly.
Yeah. So I'm a non-smooth, I did non-smooth optimization, my undergrad, or my PhD, so 0, 1 is not super bad for me.
Yeah. Well, for decision trees, we were doing all 0, 1.
Yeah.
Did you have a question?
I was just gonna ask if that natural conversion to probabilities had a straightforward interpretation with like some posterior prior sort of.
It does, and I'm gonna derive it next time. Yes. Yes.
I think this is going back to the generative additive models. So we started off, correct me if I'm wrong, we started off with defining potentially non-linear functions, univariate functions in each feature. I was just wondering, is there like a natural extension where we, say in cases when there are two features that are very similar, or just like the day before yesterday, we were doing like the XOR. So I was just wondering, does it help to also maybe have pairwise features taken pairwise and taking all bivariate functions, or does it just add complexity without really helping?
Okay, so Rich Caruana says he likes to do pairwise interactions. I've been doing fine without pairwise interactions, but we work on different types of data. Okay, I will release you because we're running late, but thank you very much. I'll see you tomorrow.